Welcome back to this module, Review of Caches. In this lesson I will describe how direct map caches are organized. In fact, a direct map cache uses the mapping cache index is equal to the block address modulo the number of cache blocks, right? Where I use the percentage sign, which is the modulo operator in C. That means that if the number of cache blocks is a power of 2, is 2 to the power of k, which it usually is, the cache index k is given by the least significant bits of the block address, right? Here we have a very small cache with 4 blocks, 0, 1, 2 and 3. The binary representation are next to it. And if we now look at block address 9, which is written in binary as 1001, the last 2 bits are used to index the cache, which is binary 01 decimal 1. The next question is, how do we know if the requested block is actually present in the cache? How do we know it's there? Right? For example, we see that block address 13, which is binary 1101, and block address 9, which is 1001, the red block and the green block, they both map to cache index 01 decimal 1. So how do we know if the green block is present in cache or the red block is present in cache? The answer is every cache block has a tag in addition to the data, in addition to the information. The tag corresponds to the part of the address that is not used to index the cache. It's the upper part of the address. For example, again we have the red block decimal 9, block address 9, binary 1001. The last 2 bits give the index 01, 1 decimal. The first 2 bits correspond to the tag, and we compare the tag stored in cache with the tag of the requested block, and if they are the same, we have a cache hit. We know the data is present in cache. To summarize these questions and answers, when do we bring a memory block into the cache? Our simplest answer is on demand, and later we will talk about prefetching, and then we start a new discussion. Where do we put it? The simplest organization is a direct map cache, meaning the cache index is given by the block address modulo the number of cache blocks. And if the number of cache blocks is a power of 2, which it always is, the cache index is given by the last k bits of the block address, which allows us to compute the index very fast. And the final question, high-level question for caches was, how do we know the cache block corresponds to the requested memory block? And we answered that question because every cache block has a tag in addition to the data, and the tag part of the block address should correspond to the tag of the cache block. There's another issue, and that's we must know if the cache block contains valid data or not. At power on, for example, all blocks are invalid, but block address 0 and cache index 0 is a valid address, right? Therefore, every cache block has a valid bit in addition to the tag and in addition to the data. This shows an organization of a direct mapped cache. At the top here we have the requested word address, and it is split up into several parts. The last 2 bits are the byte offset, right? These are needed to address a byte within a word. The next 10 bits here we use to index the cache. This indicates to us that 2 to the power of 10, 1024 blocks are in our direct map cache, and the remaining bits are used for the tag. In this case, the tag length is given by 20 bits, which corresponds to the address length of the machine, 32 in this case, minus the index length, 10 in this case, minus the byte offset, 2 in this case, and this is equal to 20 bits. right? In this example, the block size is 1 word, and that corresponds to 4 bytes in MIPS, and that equals 32 bits. This slide summarizes the equations for a direct map cache. The block address is given by the byte address divided by the size of a cache block in bytes. In other words, the bytes per block. Here the division operator denotes integer division, as in C, if all operands are integers. The cache index equals the block address modulo the number of cache blocks, and the tag corresponds to the block address divided, again integer divided, the number of cache blocks. That means that every address can be divided into several parts. The least significant bits correspond to the block offset, the most significant bits correspond to the block address, and the block address itself is split in index and tag. This completes this lesson. Thanks for watching. In the next lesson, I will show how, given a sequence of memory accesses, we can determine if each access yields a hit or a miss. Hope to see you back.